Welcome to the Types 3 session, which we're about to start. So our first speaker today is Celia Lee, who will be speaking about a complementary approach to incorrectness typing. Thanks, Celia.
It's not playing. The slides are not playing.
Slides aren't working.
Right.
Okay, yeah.
So first we start with some motivations. We want type systems that can certify both that some programs cannot go wrong, that is, there's no runtime errors, and we also want it to be able to say that some program cannot go right. However, traditional typing is about proving correctness, so if it type checks, we know it definitely cannot go wrong, but if a checker rejects a program, we usually don't know, does it really go wrong? Like in this very short expression, we are trying to do arithmetic on a non-integer, or the program actually lies beyond the reasoning power of the type system. So that program does not exist in that type system, even it will evaluate successfully. And therefore, we want some reasoning system that can offer sound incorrectness proof that if the program is ill-typed, then it must go wrong. Then we need to find some way to describe what does going wrong mean. So different typing language, for the purpose of different safety properties, there might be different kinds of going wrong. Like for the first example, we simply have a classical type safety error. Because the beta rule does not apply to the term anymore because it requires a lambda abstraction, and we might have pattern matching errors because we don't have a branch that can actually go to, and we are just stuck there. Or we may even have memory safety errors. For example, if we already after free something and we try to use it again, the operational semantics that is requiring that is requiring that the location we are trying to read all right. So since we already free it, the heap now is already empty. So we do not have the load rule does not apply to it anymore because that location is not in the domain. And in the end, we have an example of successful evaluation. So even this program has problematic branch, we never reach that branch, so it actually still evaluates successfully. And we are making an observation that a program goes wrong if it reaches a bad state. That is, it's not a value, but there's no further reduction step can make. And now we can formally define what means going wrong. That is, a program goes wrong if it's reduced to a stuck term. And as we have seen in the previous examples, this definition is capable to derive going wrong with respect to different safety properties. And now we have seen that a program's, so all normal forms can be partitioned into values and stuck terms. And these are actually dual endpoints where evaluation stops. So this suggests that we should be able to reasoning about correctness and incorrectness in a uniform way. And a type system can be a formal system for reasoning about how terms will reduce to normal forms rather than just reduce to values. And so how what how would we interpret type as normal forms? We are working in a universe of all normal forms. And we have some values, and for value types, this interpretation does not make any difference. But at the same time, we also have stuck terms that previously does not exist in the scope we consider, and it's natural to consider type that corresponds to the universe of all normal forms, and we can if we also have a type OK that classify all values, and since it's a partition, if we have some sort of complement operator, we can then describe the type that classify all stuck terms, and that type operator can be applied on any types. So if it's on int, then then that type would contain both non-int values and stuck terms. So this set theoretic models of type semantics suggest some useful tools that we can use for reasoning, and we already suggest that we already suppose we have an complement operator, and this complement operator is essential because we cannot avoid to be able to describe some negated shape constraints. For example, we may need to describe something that is not an integer, and and that is the root cause of the program go wrong. So our type needs to have some yes, it's some way to describe that so that we can reasoning about it. And sorry, I'm not sure I'm using the correct slide. Sorry, this one is correct. All right, so the set-theoretic interpretation immediately gives us two reasoning tools. First is the complement type operator, and then it's the subtyping relation calculus, and we can treat the subtyping relation calculus as some meta theory of complement type operator. And both are sound with regarding to the model, and the subtyping relation define the correct, the desired behavior of complement operator by the interplay between them. It can define some, at the base type level, we can define the disjointness, like the integer type is disjoint from an atom type, and then we can have one is the subtype of the complement of the other. And we also have the normal order reversion evolution. And using those rules of subtyping relation, we can reasoning properties about complement type operator. And we are just going to have some quick intuition check, like that for function types, we have one function type is another function type subtype if it satisfies these conditions. It's natural if you think about the set of normal form these two function types denotes, and therefore, we can conveniently have some abbreviations that we have a bottom type, which is the complement of the top type, and then the bottom to top type already denote the set of all lambda abstractions. And the other, or actually the most important reasoning tool, which is complement. This is important because refutation principles needs to be able to express negated shape constraints. for example, if we are trying to applying a non-function, then the app-e rule say that wrong application would lead to MA has type OKC. And if we're trying to do arithmetic on non-integers, by the way, this is a multi-succedent system. So this rule means if one of the argument is not integer, then we will get an error. And even for pattern matching, we need some way to say that it is not possible that match any pattern. P are patterns, and for any value that substitute to that pattern, it's impossible that M has that type, and therefore that match expression must stuck. And because we're working on the normal forms, complement would behave logically like a negation. So refuting M has type A would be equivalent with verification of the complement typing. So the complement actually offer a bridge between the proof of correctness and incorrectness. And the preservation and progress gives us give us the soundness that as long as we can prove M has type OK, then it cannot go wrong. Because any term must either diverges or evaluated. And once it's already in a normal form, the progress suggests that it must be a value. And similarly, if we can prove M has type OKC, then it cannot evaluate successfully. So for the verification rules, they're just normal rules we are familiar. And well, maybe except for the match rule. Here, the match rule, we put the M on the left because this work is actually mainly done in a two-sided setting. And we will soon see that with complement, we can we can derive typing rules of two-sided system from the normal one-sided system rules. And we also have refutation rules. So for the two-sided typing judgment, it just leaves the restriction on the left context. So now we don't require the left contexts are all variable typing. They can be terms, and these semantics intuitively should be very similar with the normal judgments. For example, for the power function, to have a type of integer, we must, it must be that the input y is an integer. However, it's not true that x must be an integer because this term always, by definition, evaluates to 1 if the second argument is 0. So because we now allow terms typing on the left as well, and because complement behavior like a logical negation, we therefore can derive some left rules or refuting rules from the one-sided system. So here, this necessity arrow is defined as A complement to B complement. It means if for the function to output an B, it must have received an A as input, and by the two complement rules, we can derive the left POPL rule for refutation from the right rule. That if we know this function only output an A when it receives an B, I forgot to mention another thing, that is for two-sided type system, we actually we can read the judgment as the typing on the left are refutation, because if we imagine the right context is empty, then the informing reading would say that if all formulas in gamma hold, then then at least one formula in delta holds. But since there's no formulas in delta, when the right-hand side is empty, it must be that the left typings are some refutation. And here, these gamma are just arbitrary, delta are just arbitrary side contexts. So we can read it as, we know the argument is not a B, and we know the function must need a B to output an A. So we reject that the application has a type of A. So this kind of two-sided rules can be derived from every one-sided typing rule, and we can view them as a kind of sequence style term typing, although it's not on the type connection. But so it's not right rules and left rules for type connection, but right rules and left rules for the type constructor. So here, the left is in left rule for the constructor of application, and the right is in right rule of the constructor of complication. Since our system is trying to do constructive proof and refutation at the same time, we realize that there's a kind of well-studied logic that do similar things, which is called bi-intuitionistic logic. So this is a kind of logic that has a combining power of both intuitionistic logic and co-intuitionistic logic, while intuitionistic logic is for constructive proof and co-intuitionistic logic is for constructive refutation. And usually the bi-intuitionistic logic reasoning system is often present as some sequent calculus style rules, and we realize that it is also the case for our two-sided system, that it looks like kind of some sequent style of term typing, and therefore when we are considering about the necessity type for function refutation, we first realize that it does not compose well. Oh yes. So we can have the current function for the arrow type that we have two we have two arguments at the same time. So I forgot to put the current rules on the slides, but inspired by the co-arrow in the co-arrow in the bi-intuitionistic logic, we define a co-arrow type as the dual counterpart as the arrow type, and with this definition, we can derive left rules that have lambda terms carried just like the normal arrow type, like they would at the right.
Sorry, we're going to have to.
Oh yes. Oh yeah. So these are the two most messages I want to express. One is type should. We can interpret a type as a set of normal forms, so that through complement we can have a formal reasoning system for both correctness and incorrectness, and the complement yields a co-arrow which can be viewed as the type counterpart as the co-arrow in the co-intuitionistic logic that can compose us when we are refuting okay.
I think, could the next speaker start to get ready? And if we have one question while they're getting ready, that would be great.
Have you considered implementing the type system to play with it? Do you have an implementation?
No.
Okay, well, thank you very much.